Welcome back. In the previous lecture, we had introduced Laplace operator and the definition of harmonic functions. In this lecture, we are going to relate harmonic functions with holomorphic functions and also give give notions on how to solve Dirichlet problem in 2 dimensions. So if you have a holomorphic function and if u and v are its real part, then it turns out that the real parts, u and v are real and imaginary parts, then it turns out that both the real and imaginary parts are harmonic functions. This is a very simple consequence of the Cauchy-Riemann equation. For instance, if you take the real part and if you look at the Laplacian of the real part, which is this uxx plus uyy, and by Cauchy-Riemann equations, ux is vy, so you use that information here, and then uy is minus vx, you use that information here, and this difference is 0 because this is the mixed partial derivatives, and the partial derivative, and for a holomorphic function the partial derivatives of the real and imaginary part are actually continuous. So this shows that the real part of an holomorphic function is harmonic. Similarly, you can do the same thing for an imaginary part. So the imaginary part is also harmonic. So for any holomorphic function, the real and imaginary part are harmonic functions. Converse is more or less true in the sense that if you take any harmonic function, then it is a real part of a holomorphic function, or equivalently you can say it is the imaginary part of a holomorphic function. But we have put this condition of the simply connected domain only to ensure, because the problem is that most of the harmonic functions are real part of some holomorphic function, but it can happen that the holomorphic function is actually multi-valued. So to avoid that is why we have this extra hypothesis. So in this case, you can avoid this multi-valuedness problem. For instance, look at this function uxy, which is a harmonic function, that is half log x squared plus y squared. And this is the real part of log z, and this is defined in the punctured plane c minus 0, which is not a simply connected domain, it's a non-simple connected domain. And the reason is because of this multi-value. However, if you restrict this to a simply connected subdomain on which log z is single value, then it's a holomorphic function and it makes perfect sense. So in that sense, any holomorphic function is also the real or imaginary part of a any harmonic function is also the real and imaginary part of a holomorphic function. Okay, which means there is a kind of a one-to-one correspondence between harmonic functions and holomorphic functions. In fact, if you are given a harmonic function, you can introduce what is called a conjugate harmonic function, which is the solution, which is the one that you obtain by solving the Cauchy-Riemann equation. So given a harmonic function, you can use the Cauchy-Riemann equation to solve for the conjugate harmonic function. So given u, we use Cauchy-Riemann equation to solve for v, and v will also be a harmonic function, and u plus ib will be a holomorphic function. So there is this nice correspondence, which means the way we were asking this question in the previous lecture, can we classify all two-dimensional harmonic function? We have not given a formula like we did in one dimension, ax plus b all straight lines. We don't have such a specific formula, but we seem to have identified the class of two-dimensional harmonic function, which is precisely all holomorphic functions. Okay, fine. Now, if you have done a course in partial differential equation and or on some study on harmonic functions, you must have come across the properties of harmonic function. And the fact that there is a relation between harmonic function and holomorphic function is also visible in the results and properties that you prove. For instance, you must have proved the mean value property for harmonic function. You must have proved the Cauchy integral formula for holomorphic function. They are precisely the same property. That is, you have this connection. Like you have this maximum principle for harmonic function. You have a result of maximum modulus theorem and Liouville's theorem for this holomorphic functions. All these are similar results. I mean, they are of the same nature. So they precisely say the same property about these functions. It's just that they are said in different languages and different subjects. Whereas in when you do this in harmonic setup, you just don't do it in 2 dimension, right? You do it in higher dimension, like this mean value property or this maximum principle are all valid in the higher dimension, not just n equal to 2. Whereas when you do this in for holomorphic functions, these things you do for 2 dimensions. But there is this connection, you see that. So if you need to classify harmonic functions, you just need to know holomorphic functions and vice versa. So let's look at some examples of holomorphic functions, because by looking at examples of holomorphic functions, we also have examples of harmonic functions. This is the reason I had pushed it to this stage, and we did not give examples when we defined holomorphic function. Only, one, because you have come across this notions before. Secondly, I wanted to bring it here so that I can show you both the holomorphic functions and the harmonic functions. So consider the complex polynomial z power alpha. Okay. Now, of course, you can also have alpha to be complex, but in that case, you can separate the real and imaginary part and write it as z alpha into z power I beta and so on. So let's, without loss of generality, look at what happens when alpha are real. So z power alpha, using the polar form for z, where r is the magnitude and theta is the argument, you have r alpha ei theta alpha. But you see this theta, the range, the domain of this theta has to be of length 2 pi, right? For any interval, if theta is coming from a domain of length bigger than 2 pi, then you have more than one representation for the value z. So if theta is coming from r, let's say, the entire real line, which means that z power alpha is also this quantity for each integer k. So if you simplify this, you actually get z alpha is ei 2 pi k alpha for all integer k, which means that one z has multiple representation in terms of the argument. So if this is not 1, if ei 2 pi k alpha is not 1, then z alpha is not single valued, it's multi-valued, right? That is how you come up with multi-valued functions. So something like that happens even for complex polynomials here. Like if you take, for instance, alpha to be an integer, then k alpha is integer, then this ei 2 pi k alpha is actually 1. So in that case, z alpha are all single values. So whenever alpha is an integer, z alpha is single value. For positive integer alpha, z alpha is holomorphic everywhere in C. Let me show that. Okay, so it's a holomorphic function. For positive integer, it's a single value, so it's holomorphic in the entire C. So its real and imaginary part are actually harmonic functions, which is r alpha cos alpha theta, r alpha sin alpha theta. So for every positive integer alpha, z alpha is a holomorphic function, and you have the real and imaginary part as harmonic. So we have so many harmonic functions already, just from the complex polynomials, right? For instance, as a particular case, you can think of z square, where alpha is 2, Z square is a holomorphic function. Its real part x square minus y square and its imaginary part 2xy are harmonic functions. Now when alpha is negative, then you have a singularity at z equal to 0. So the z power alpha is holomorphic in C minus 0. We have already seen one example in previous lectures some time back. The case when alpha is minus 1, you have this 1 over z function which is holomorphic except at 0, and it was actually a map which was inverting about the unit circle, right? We have shown this already. So this is a holomorphic function, so except at 0. So except at 0, the real and imaginary parts are harmonic functions. So one more example, and this is true for every negative integer alpha. When alpha is irrational, we have that z alpha is multi-valued, because when alpha is irrational, k alpha will take ei 2 pi k alpha will take different value for each k. So you actually have infinite number of values. So z alpha actually becomes multi-valued there. When alpha is rational, it's of the form p by q, where both p and q are co-prime, then again z power alpha is multi-valued, but this time it takes exactly finite number of values. In fact, it takes as many values as the denominator of the rational, that is q. The p doesn't play any role, the q. So z alpha is multi-valued and takes exactly q different values corresponding to the q roots of unity. So these are all these two are multi-valued functions. But you can restrict them using branch cuts and so on, and to make it single value. Now then, and by the way, just to highlight you, this is not something new as well, right? This was happening also in real line, right? For instance, if you take the square root function, right? Square root, you have both positive and negative square root, right? For instance, the square root of 4 is both plus 2 and minus 2. Right? So you also have real functions which are multi-value, and you have to make it single value, you would have to restrict your domain. So you either look for some segment, only one part of the, you only look for positive roots or negative roots. So you restrict like that, right? So this is not, so this is the case even in the real case. That's what I just want to highlight. So it's not something new. Here you have but here even other things, there are even other interesting stuffs which became multi-valued. So one example, I mean, let's look at other examples of holomorphic functions. The extension of the exponential function. So how do you define a exponential function of a complex number? Is by the power series. Okay, and this you can see immediately that it's not an injective function. That is, many points in the domain can go to one point in the range. That you can see immediately here, right? So you take any z and you take z plus I2 pi k. Both are different values. Both are different complex numbers, whereas they take the same value, which is e power z, right? Which is because for any integer k, this value is going to be 1. I mean, the e power of that is going to be 1, right? So this is a holomorphic function. So its real and imaginary part are going to be harmonic function, and the real part is e power x cos y, and the imaginary part is e power x sin y. Then you can also define this trigonometric function, extend the notion of sine and cosine to complex numbers. That how do? You do it using the exponential function. So cos z is e power iz plus e power minus iz over 2 sine z is e power I z minus e power minus I z over 2y, and so on. Right. So these, one can show that these are also holomorphic function and its real and imaginary part, which are given here, which involves the cos hyperbolic function, sine hyperbolic functions. These are also harmonic functions. So you have so many examples of harmonic functions just by knowing holomorphic functions. Right? Then the log function, extending the logarithm to complex numbers. Now you think of log as the inverse of the exponential function. You define log as the inverse of the exponential function, right? So, but you have already seen that exponential function is not injective. So its inverse has to be multi-valued, which it is. So the log z is log r plus I theta. It is not defined at z equal to 0, so it's holomorphic except at z equal to 0. It's multi-valued because if you see that for z, as I said, if you change the argument by an integral multiple of 2 pi, the z value, so the z is same. Whereas in the log z, you are going to get I 2k pi. So it's a different value. It's not the same value as well. So for the same z, you have infinite number of as many values as k here. Right? So for each k, there's a different value. So it's a multi-value function. Of course, if you restrict yourself to a domain of say minus of theta in the range of minus pi to pi or some interval of length 2 pi, then you can make these functions a single value as well. So some nice property of this log is that which we don't have in the real case, that you know that the real logarithm of 1 is 0. So log of 1 is 0, whereas in the complex extension actually tells you that log of 1 is 0, but log of 1 is also all these complex numbers. So when k equal to 0, you get the 0 value, but for k non-zero, you have I 2k pi. These are all log 1s. Similarly, you can also define the logarithm of negative numbers using this extension, right? So whenever x is negative, you have this value from this definition here. Right? So these are advantage of extending these classical notions from real variable to complex variables. Okay. So now we have enough examples about harmonic functions. Now let's get into what is called the Dirichlet problem. A Dirichlet problem is a boundary value problem. What it basically says, so basically a condition like this on the boundary of a domain. So if omega is a subset of Rn, okay, let's say it's an open subset of Rn. You can even assume connectedness, okay, open domain of Rn. Then and if g is a given function on the boundary of that domain, then you are looking for a harmonic function which takes the value g on the boundary. Okay, yes, such a condition is called a Dirichlet condition, which is why the problem is called a Dirichlet problem. This is a boundary value problem. The unknown is the u harmonic function. You are looking for a harmonic function which takes the desired value on the boundary. Okay, this is something you try to do in a course in a PD. If you have seen a course in partial differential equation, you solve. So this is a second order partial differential equation. In fact, this is an elliptic equation. Like Laplacian is an elliptic equation. So this is a second order elliptic equation. But now using the complex function theory, we can actually solve this problem in the case when n is 2. That is in the 2 dimension, you can solve this for a large class of domain omega. Okay, and what is that? That is this. So in 2 dimension, you can solve this equation 3.1 just by solving the case when omega is the unit disk, open unit disk. That means solving this problem for some domain, and we are going to tell you what that domain is. For some domain, it is enough to solve this problem in the unit disk D, which is mod z less than 1. And this is a consequence of the very nice classical result by Riemann. It's called Riemann mapping theorem. And what does Riemann mapping theorem tell you? It tells you that every simply connected proper subset of the complex plane, so let's call it omega. So every simply connected proper subset of C is conformally equivalent to the unit disk, to the open unit disk. So basically it says that every simply connected proper subset, okay, it's not, you cannot take the full complex plane. Any proper subset which is simply connected is conformally equivalent to the unit disk. And what does conformally equivalent mean? Means that there is a holomorphic function which is a bijection from the set to the unit disk such that the inverse is also holomorphic. So it's called biholomorphism. Okay. And we have already talked about conformal maps, right? So basically holomorphic function, even the fractional linear transformation, these are all conformal maps, right? So so here when they say conformal equivalent, they mean there is a biholomorphism between the given set omega, which is simply connected, and the unit disk. Okay. As such, there is no uniqueness of this biholomorphism. There are lots of there could be infinite number of biholomorphism from omega to b. That doesn't matter, but you can make it unique. So they depend on two parameters, and once you fix these parameters, then the holomorphism can be fixed uniquely. One is that if you pick a z naught in omega, and if you demand that that z naught is mapped to the center of the unit disk, and the f prime of z naught is positive for is positive. I don't know what is no, f prime of z naught is positive. Then this for all z doesn't make sense here. Okay, don't worry about that. What we are saying here is that if for each z naught of omega there is a unique biholomorphism such that that z naught is mapped to the center and f prime of z naught is positive. So once you fix z naught and once you demand that f prime of z naught is positive, then you can pick one unique biholomorphism from all possible biholomorphisms. So which means that if you take a set omega, you can actually map every element. So you can actually find a conformal map such that so for each z naught you can find a conformal map which maps the z naught to the center of the disk. Okay, and here you see the unit disk is bounded, whereas we don't have any such assumption on the omega. Omega could be an unbounded set. It's only a proper subset, but it could be an unbounded subset. Okay, but that unbounded subset is conformally equivalent to the bounded set and bounded disk, bounded unit disk. So using this theorem, what we are saying is that if you want to solve 3.1 for any arbitrary domain omega, you just have to solve it in the unit disk. And since there is a conformal map from omega to C, you can actually convert the solution on the unit, use the solution on the unit disk to actually compute the solution for any simply connected proper set omega. So let's explain this in more detail. Firstly, what are all the conformal maps from the unit disk crystal? So I said that the conformal map in the Riemann mapping theorem is actually not unique, right? That biholomorphism is not unique, and that you can actually see very easily by actually looking at all the conformal maps from the unit disk to itself, right? Because for instance, suppose there is say one map. Suppose say there is one biholomorphism from omega to d, and if there is another biholomorphism from d to d, that is unit disk to itself, then the composition will give you a new biholomorphism from omega to d, right? So actually the multiplicity of biholomorphism from omega to d is actually depending on the multiplicity of biholomorphism of uh, um, from D to D, from unit disk to unit disk. So that's what I'm explaining here. That you take the unit disk D, you fix any point Z0, then this map TZ that we have given here, is a map from D onto itself, and it's such that this Z0 is mapped to the origin. So for each Z0 you have a different map. So when and you can see here that the Z0 T of Z0 is Z0 minus Z0. So that maps to the origin here. Okay. So now you can actually even do something further. You can even rotate this map. See, it's a map from the unit disk to unit disk, right? So you can actually rotate this map, and any rotation of this map is also a conformal map from unit disk to unit disk, because rotation is not going to change the angle, so it still remains conformal, right? And what is rotation? I said in the setup of complex numbers, rotation precisely means multiplying by a complex number on the unit disk, right? That's what we had seen in some earlier lecture. So rotating a map basically means multiplying by a complex number of modulus 1. So the map will still works if you compose with rotation, which means that if you take any theta in from minus pi to pi, you have the same z0 which you fixed, and you just multiply this t map by this e power I theta for any choice of theta. You fix a theta, you do this. So you are rotating by an angle theta. That's it. Okay. So this is a new map now. This is also a conformal map, because this is because the original one was a conformal map because it's a fractional linear transformation, right? So that form. So this is a conformal map, and then you're composing with another with rotation. That's also a conformal map. So for every fixed z0 and theta, you have a conformal map from D onto itself. You have so many conformal maps, which means that once you fix a z0 and theta, there is a unique biholomorphism from D onto itself, where the z0 is mapped to the origin and T prime of z0 is possible. Okay. So now, this means that solving this Dirichlet problem in any arbitrary domain is equivalent to solving it on a disk. So natural question is, can we solve this problem when omega is d? Okay, that's a natural question that we can ask, and that's what we are addressing now. And this is a very famous result you must have done in your probably a BD course, and there is what is called the Poisson formula for the disk, for a two-dimensional disk. So if you take the unit disk in R2, which is what we did, I mean mod z less than 1. So if omega is your unit disk, and if g is a continuous function on the boundary of the disk, then there is a unique solution to the Dirichlet problem. 3.1 is the Dirichlet problem that I showed you, that is Laplacian u equal to 0. On the boundary, it's equal to g. So that problem on the unit disk when omega is d admits a unique solution. Okay, this is something I'm sure you must have done in a course in your first course in BD. Actually, the proof is by separation of variable. So the idea is this, that you are in two dimension, since your since you are on a circle which is on a disk, you rewrite 3.1 in the polar form, in the polar form, okay, which is the 3.2 given here. So this is the polar form of the Laplacian here with the boundary condition. So this boundary condition basically means the periodicity condition of the theta variable, because now theta is the argument, and this is the boundary. So this is the condition on the boundary of the circle. So here omega is the unit disk D. So 3.1 can written in the polar form, and then you use the separation of variable. So when you assume this fact that so variable r and theta and u can be separated. So use separation of variable, plug it in here. You will solve some eigenvalue problems and use it to solve some second order ODE and so on. So once you solve that and of course then use the boundary condition, use the Fourier series and so on, then you get a solution. Now the beauty about this is that for separation of variable, we assume that the solution is in the form of separated variable, and that looks like an assumption. Yes, it is an assumption, but the fact that the equation 3.1 or even the 3.2, which is equivalent equation, has unique solution means that the solution that we find after we separate variable is actually the only solution. So basically the idea is that the Dirichlet problem has a unique solution. Okay, for bounded domain it's a unique solution. For unbounded domain also it's unique solution if you impose a condition at infinity. Okay, so there is a unique solution to that Dirichlet problem, which means that by guess or by hook and crook, if you arrive at a solution, that is the only solution. Right? So now when you do a separation of variable technique, you arrive at a solution. By uniqueness, that should be the only solution. So you have obtained a solution. So by doing separation of variable, you can actually derive this formula for the solution U, which is called the Poisson's formula. And what you have here, 1 over z minus ei theta, that is what is multiplied with g, this one. This is what is called the Poisson term. Okay, so this is the Poisson formula. So this is the solution. So this is the formula for U on the unit disk. So we have solved the Dirichlet problem on the unit disk. So how do you solve it for any arbitrary simply connected subset of R2, proper subset of R2, right? By Riemann mapping theorem, we have once, right? By Riemann mapping theorem. So Riemann mapping theorem tells you that it is enough to solve it in the unit disk D, okay, as long as you know the conformal mapping from omega to D. So basically, solving the Dirichlet problem. So the difficulty in solving the Dirichlet problem in 2 dimensions is now reduced to the difficulty of finding the conformal mapping between omega and D. So basically you have solved what we have said. If you solve in the unit disk, you have solved the Dirichlet problem in omega. But the difficulty is to find the conformal map. Wherever you can find the conformal map explicitly. So for all domains, you may not be finding the conformal map may not be easy. Right? So whenever you can find the conformal map between omega and D, since you can solve the Dirichlet problem in D, you can solve the Dirichlet problem in omega, as long as you know the conformal map. Now this requires this notion, because when we solve it, so when you find a harmonic function in D satisfying G on the boundary, what you are saying is that you take that harmonic function, you compose it with the conformal map which is from omega to D, and that composition should also be a harmonic function, right? Only then you have solved it in omega. So let's say if U is a harmonic function from omega 1, okay, so you can think of omega 1 as your unit disk D, and if D is a holomorphic function from omega 2 to omega 1, so omega 1 is your D, omega 2 is any arbitrary omega. If D is holomorphic, then U composition T is harmonic in omega 2, okay, and this you can see very easily, because see, what is U composition T? U composition T is the real part of the holomorphic function function u plus iv composed with t. See, what is given? U is given to be harmonic. And what did we say? If u is harmonic, there is a corresponding conjugate harmonic function that you obtain by solving the Cauchy-Riemann equations. So given u harmonic, you have a conjugate harmonic function v. Once you have u and v, you can write down the holomorphic function u plus iv. And that is this u plus iv. So u plus iv is a holomorphic function. T is the conformal mapping from omega 2 to omega 1, which is a holomorphic function. So T is a holomorphic function, u plus iv is a holomorphic function. The composition is also a holomorphic function. And what is the real part of this composition? The real part of this composition is u composed with T. So the real part of any holomorphic function is harmonic, which means u composed T is harmonic because it's real part of a holomorphic function. So you started with u a harmonic function, T a holomorphic function, then u composed T is a harmonic function in omega, and that is what justifies what we are saying here. If you solve for a harmonic function or the Dirichlet problem on the unit disk T, and if you have the conformal mapping T from omega to B, then u composed T is actually it's actually a harmonic function on omega. Now in this case, you see this result is not true when you do the other way, like T composed u is that result is not true. In fact, this result is true. You remember that we are in 2 dimension, right? All these omega 1, omega 2 are all subsets of R2 or C. So this result is valid in 2 dimension, because when you say harmonic, you mean Laplacian u equal to 0, right? So in the case of 2 dimension, this result is true, that is harmonic and holomorphic composed gives you harmonic. In higher dimension, this result is not true. In higher dimension, you have to replace this Laplace operator in the harmonic function definition with what is called n Laplacian. So in the n dimension, you should replace the Laplace operator with n Laplacian, which is generalization of Laplacian. It's a non-linear operator, and for such operator, this result is true. This composition respects that. But for Laplacian or an harmonic function, this result is not true in higher dimension. Similarly, as I said, even the T composed U, that result is not true. Anyway, that's just extra information. Don't worry about it. So using this to result and the previous solution, as I said, you can, so if given a conformal mapping T from omega to B, such that the boundary of omega is matched to the boundary of the open disk, then the solution to the Dirichlet problem on omega is given by U composed T. So if U is the solution, U given by U composed T, okay, where U is the solution on the unit disk. Okay. So now I'm giving some examples of conformal maps between some proper subsets of C to the unit disk. For instance, this is a conformal map which maps the right half plane to the unit disk. So you see this is an unbounded subset of C. Right half plane is unbounded. Right half plane means that real part is strictly positive. So right half plane is mapped to the unit disk. This is a conformal map. How do you find this conformal map? You can actually fix uniquely. So if you fix 3 points and you say that you want to map these 3 points uniquely to 3 points in the range, and you can using this information you can actually write down uniquely a fractional function or this Mobius transformation, right? That is a conformal map that you will get. That is how you get these maps. So you want to map, say, 1.20, 1.21, and another point to infinity. To fix these 3 points, then that's enough to uniquely determine the conformal map, which takes these 3 points to the decide points. So this is a conformal map which maps from the right half plane to the unit disk D, an unbounded set to the bounded set. You see. something that I pointed out earlier. Now this is a example of a conformal map which maps the upper half plane to D. How do you get this map? So you see, you have this map from right half plane to D, and you know that if I rotate right half plane counterclockwise by an angle of pi by 2, I get the upper half plane. So what you need to do is you have to rotate this, or you have to compose this conformal map with 90-degree rotation. 90-degree rotation is basically means multiplying by the complex number I. So if you multiply the complex number I to this map, this is precisely what you get. This is the map that you get. So this is the map which conformally maps the upper half plane to the unit disk. This is what I explained. So this is obtained by rotating the right half plane by pi by 2, which means you are composing this map z minus 1 over z plus 1 with the rotation map, which is multiplication by I, rotation by 90 degree. This is the map which conformally maps the first quadrant of C to the unit disk D. Again, how do you get this? We already know, we have seen in some previous lecture also that the z going to z square map maps the first quadrant to the upper half plane, and you already have a map from upper half plane to D. So what you need to do is compose this map, upper half plane to D map, with z to z square map, and that's precisely what you have done here, and we have this conformal map from first quadrant to unit disk. This is a conformal map which maps the horizontal strip minus pi by, that is the imaginary part is lying between minus pi by 2 to pi by 2 to the unit disk D, and this is again we obtain um, by composing this first map, this right half plane with with e power z map. So because this z going to e power z, this again I have shown you a picture in the earlier lecture. Z going to e power z maps the strip to right half plane, and you have this right half plane to D map here. So you compose this map and this map, e power z map, you get this map. So this is a conformal map from the horizontal strip to the unit disk. So with that, we complete. We have given the relation between harmonic functions and holomorphic functions, and how to solve Dirichlet problem in 2 dimensions, and so on. Now here what we have is I've given you an exercise. So here you see, though the statement of the Poisson kernel had said that G has to be a continuous function on the boundary of the domain. Here I have given you a case where G is actually a step function. So the boundary data is actually a step function, and I am asking you to, and the domain omega is given to the upper half plane. So we have already given you this map from upper half plane to disk. So use this information. So you solve the Dirichlet problem in the upper half plane with this G, which is actually like a step function. For positive it's 0, x it is 0, for negative x it's 1. Just for you to verify, I'm telling you. So this is the solution to this problem. You can see that immediately, right? So you see when x is positive, it is the so in C it is the positive real axis, which is of angle 0, right? Whereas the negative real axis, which is x less than 0, negative real axis is of an angle pi, right, with that orientation. And on positive, it takes the value 0. So when the angle is 0, it takes the value 0. When the angle is pi, it takes the value 1. So the solution is actually theta. I mean, at least from the boundary condition, it looks like this is one possible choice, theta by pi. Right? You can verify that, and if you define this, you can actually verify that this will be a solution. Please obtain this using the method that I solve it in the disk, use the map from upper half plane to disk, and try to obtain the solution. And this is a harmonic function because it's a real part of this holomorphic function. Okay, try doing this as an exercise. Also, I have not proved the Riemann mapping theorem in this lecture here. You can take that as a exercise as well. You can try looking for a proof of Riemann mapping theorem. Sometimes later in the course, if we can get to prove it, I will try to prove that. As I said, I'm not following any logical order, so uh, like for instance, I will define simply connectedness and everything in a future lecture, though we have used it in this lecture. So we are not following that logical structure as I had already announced in the first lecture. So try solving this. Also try looking for a proof of the Riemann mapping theorem. Also try to fill the proofs or gaps of whatever I say. If I don't prove things very explicitly or state it explicitly or something, try proving it if you have not seen it before or not, or if you don't know it, or if you don't know it already. Okay. So with this we finish this lecture. I'll see you in the next lecture. Thanks a lot.